Deep learning models rely on backpropagation. To learn, they freeze their forward operation, calculate the exact error at the output, and propagate a global update signal backward through the entire weight matrix. Biological brains cannot do this. There is no global backward pass. Real neural networks learn through local rules, like Spike-Timing-Dependent Plasticity. A synapse updates its own strength using only the chemical and electrical signals immediately available in its exact physical location. Pioneers of backpropagation, like Geoffrey Hinton, have attempted to build artificial networks using purely local rules. Historically, these local systems fail to scale. Without a global error signal, they struggle with credit assignment across deep layers and fall behind the performance of standard backprop on major benchmarks. These neuron-only models ignore the physical space between synapses, a space occupied by the glial network. In biology, this parallel computational substrate monitors, prunes, and reorganizes neural circuits in real time. Glial cells outnumber neurons in many brain regions. They operate through chemical multi-channel signaling and physical mobility, forming a parallel system that provides the multi-timescale coordination required to make local learning work at scale. Unlocking biological efficiency in AI requires abandoning static mathematical matrices in favor of dynamic, physically embedded spatial networks. This research plan charts the transition from standard spatial embedding to full physical simulation, establishing a 4-phase roadmap to test where glial mechanisms provide computational value. We begin with Level 1, a null-space simulation. The network uses instantaneous connections, but we apply spatial geometry to dictate how weights learn, isolating the benefits of spatial coordinates. The destination is Level 3. At this fidelity, signals propagate as continuous physical waves through a 3-dimensional grid, interacting with dynamic chemical fields that evolve at their own independent rates. Simulating continuous space carries a heavy hardware cost. Moving to Level 3 introduces a 100 to 1,000 times computational overhead, requiring dedicated GPU clusters to solve the reaction-diffusion equations coupled to the neural signals. This project follows a strict gating criteria. We only escalate to the next level of simulation fidelity if the current level produces a qualitative change in behavior that cannot be achieved by simply adding more parameters to a standard model. The first engineering step assigns 3D spatial coordinates to every weight in a standard network. Physical proximity now corresponds directly to gradient correlation. We then overlay a reaction-diffusion equation across this geometry, creating a continuous field for spatially smooth, temporally persistent learning rate adaptation. This field functions as an artificial astrocyte layer. In biology, astrocytes coordinate synapses within their local physical territory. In our network, the field creates a slow modulatory layer that correlates the plasticity of spatial neighbors over long training cycles. As the network processes data, the field responds to activity. Without any hard-coded boundaries, it allows the network to spontaneously self-organize into specialized functional domains, periodically focusing plasticity where it is most effective. Isolating this spatial geometry inside a standard backpropagation framework establishes whether physical embedding alone improves learning efficiency, providing the baseline required to justify deeper biological mechanisms. This graph plots diffusion rates to identify the primary risk of coupling gradient descent to a spatial PDE. If the diffusion rate D is improperly tuned, the system enters a Turing instability. Outside of the safe zone, the modulation field collapses the network's pathing. Maintaining stability requires finding the intermediate range where spatial coupling creates structure rather than noise. We then introduce emulated microglia. In the brain, these are highly mobile cells that continuously survey the neural tissue. In our system, they act as mobile computational agents that patrol the coordinate space, monitoring connection health. These agents use chemotaxis to migrate toward high-error regions. By clustering around synapses with conflicting gradients, they selectively eliminate the weights causing the most instability. Standard magnitude pruning blindly removes the smallest weights based on a global threshold. The microglial agents perform targeted, spatially informed structural remodeling, evaluating every connection within its local functional context. If the combined effects of astrocytes and microglia improve convergence with less than a 20% compute overhead, the first phase is complete. We then move to the removal of backpropagation. Phase 2 severs the global backward pass. Weight updates are replaced entirely by localized Hebbian learning rules, where each synapse relies only on the information available at its own physical location. Testing these local rules in isolation confirms they are insufficient for deep credit assignment. Without coordination, learning becomes chaotic. The biological solution is the astrocyte third factor. In the brain, astrocytes release D-serine, acting as a mandatory co-agonist for synaptic change. Without it, local Hebbian learning simply doesn't happen. In this framework, astrocytes are not modulators, they are constitutive. They determine exactly which synapses are permitted to learn at any given moment, providing the gating signal that focuses plasticity on relevant active domains. If this local rule and glial gate combination can match standard backpropagation, it validates the biological argument. Glia evolved as the specific architectural solution to the credit assignment problem. Phase 3 introduces discrete propagation delays. Signals no longer teleport. They traverse fibers at finite speeds, arriving at neurons at different times. Emulated oligodendrocytes manage this timing through adaptive myelination. By adjusting conduction velocities, they control when signals arrive, which fundamentally changes how the network computes using spike-timing plasticity. This leads to the Phase 4 decision, whether the continuous interaction between signals and glial fields during transit justifies the cost of a full physical simulation engine. We compare the two paradigms. Level 2 uses delayed teleportation, where signals jumped from point A to point B after a set time. Level 3 simulates a continuous wave that interacts with reactive fields along its entire path. We only build the optimized Level 3 engine if the continuous in-transit interaction produces behaviors impossible in simpler models, such as spatial filtering or wave resonance within the medium itself. Reaching this final stage would confirm that advanced artificial intelligence requires signals to traverse a dynamic physical medium in real time. When the full glial ecosystem is coupled to a neural network, the system exhibits continuous architecture search. The network shape becomes a dynamic variable. Neural updates handle immediate data processing, while the slow-moving glial fields and mobile agents continuously reorganize the connections. The network grows where signals are consistent and dissolves where they are redundant. This physical remodeling protects against catastrophic forgetting. Standard networks overwrite their past knowledge to learn new, conflicting tasks. A Glia-Augmented system structurally isolates historical data. By pruning idle connections and locking in established timing pathways, old knowledge is preserved in the spatial topology of the network, rather than being stored solely in fragile parameter values. This shift means the network doesn't just memorize data, it physically rebuilds its own hardware topology to match the landscape of the incoming information. The project's final goal is a standardized library of composable, brain-like software structures. These pre-configured modules can be assembled into unified cognitive systems. Each module contains neural architectures and glial parameters tuned for distinct roles. An emulated visual cortex will have different spatial geometry and pruning schedules than an emulated hippocampus. Standard artificial networks are mathematical optimizers. Biological networks are dynamic, multi-timescale ecosystems that modify their own physical properties based on local constraints. Biology solved its scaling bottlenecks by leveraging the physical space between synapses. Chemical fields and cellular migration transform this space into a parallel computational channel. Backpropagation established the current dominance of global optimization, but pushing artificial intelligence further requires embracing the structural, spatial, and temporal reality of the biological brain.